Hello and welcome back to set theory. In the last few lectures, we talked in depth about set unions, which correspond to logical OR, as well as set intersections, which correspond to logical AND. Today, we're talking about symmetric difference, which is this little A triangle B thing. This corresponds to logical XOR, or exclusive OR. And so what XOR or exclusive OR means is exactly one of these is true. So either X is in A or X is in B, but not both. And we can visualize this with a Venn diagram. If the circle on the left is A and the circle on the right is B, then the symmetric difference of A and B is just this red area here. So it's anything that's in A or in B, but not in both. But now you may be asking yourself, how do we know this set actually exists? Well, here's the thing. We can rewrite it like this, since whenever this part's true, whenever X is in A or X is in B, but not both, well, this condition implies you have to be in the union anyway. We know this set exists by the axiom schema of separation, so therefore this set has to exist as well. There's also a theorem that says the symmetric difference is just equal to A union B set difference with A intersect B. Why is that true? Well, being in this set means that you're in this set, but you're not in this set. In other words, you're in at least one of A or B, but you're not in both A and B at the same time. So therefore, to be in this set, but to not be in this set means that either you're in A or you're in B, but you're not in both. So these two sets have to be the same. And now there's another theorem that says the symmetric difference is just A difference B union with B difference A. In other words, to be in the symmetric difference, that's the same as saying you're either in A but not in B, or you're in B but not in A. Thinking in terms of the Venn diagram, either you're in A but not in B, this left half, or you're in B but not in A, this right half. So therefore, these two sets have to be equal, since to be in A but not in B, or to be in B but not in A, well, that's logically equivalent to saying that you're in A or you're in B, but you're not in both. And by the way, I think a lot of books give this as this definition of symmetric difference instead of this. However, in my opinion, this one's more intuitive. So let's prove some properties, such as the commutative law, so it doesn't matter which order you do it in. Why is this true? The left side can be rewritten like this, and the right side can be rewritten like this. Now, saying that you're in A or you're in B, but you're not in both is logically equivalent to saying you're in B or you're in A, but not in both. So since they're logically equivalent, these two sets have to be equal. Symmetric difference also obeys an associative law, saying that we can move the parentheses around and it doesn't matter. Why is this true? Well, if X is in this guy, what's that the same as? Well, that's the same that X is in exactly one of these two sets. In other words, X is an element of the first set, exclusive or X is an element of the second set. But now we can rewrite this part. This part is the same as saying X is an element of B, exclusive or X is an element of C. But now exclusive or is logically associative, so we can move the parentheses. But now this part right here is the same as saying that X is in the symmetric difference. So saying that X is in this set, exclusive or X is in this set, is the same as saying X is in the symmetric difference of those two sets. So X is an element of A, symmetric difference B, parentheses, symmetric difference C. So since these two sets have exactly the same elements, they must be equal. So this theorem tells us it's safe to write something like this without parentheses, since the order of the parentheses doesn't matter. So this would be the set of things which are in exactly one of these three sets, A, B, C. Now here's an exercise. What's the symmetric difference of any set with itself have to be? Pause the video and think about it. Okay, ready for the answer? The symmetric difference of any set with itself is just the empty set. But why is that? Okay, well, here's the thing. Symmetric difference is just this set, right? But here's the thing. This part right here is always false. And the reason it's false is because this is the same that exactly one of these possibilities has to be true. And that's impossible because either they're both true or they're both false. So the set of all x for which false is true is just the empty set, because there's nothing that could ever make that true. Here's another exercise. What's the symmetric difference of any set with the empty set? Pause the video and think about it. Well, it turns out the answer is just A. But why is that? Well, we can write this guy like this, but now we can simplify this logical expression. You see, this part is always false since the empty set has no elements at all. But now saying exactly one of these two possibilities is true is logically equivalent to just saying that this one's true, because we know that the second one's automatically false. So therefore, this part simplifies to x is an element of A. And so now the set of x for which x is an element of A is just A. Now here's a neat little theorem. It says two sets are equal if and only if their symmetric difference is empty. Let's prove the forward direction first. Assume A and B are equal. Well, if A and B are equal, then A symmetric difference B, well, we can just substitute, make them both A, because they're equal. And then what is this the same as? Any set symmetric difference with itself is just the empty set. So this is equal to the empty set. So we see that if this is true, then this has to be true. Now let's prove the converse direction. Assume that this is true. Assume the symmetric difference is the empty set. And what do we want to show? We want to show that A equals B. Let's proceed by contradiction. Towards a contradiction, assume that A and B are not equal. Well, since they're not equal, then that means either A has an element which isn't in B, or B has an element which isn't in A. So either A has an element which isn't in B, or B has an element which isn't in A, or possibly both. Well, if A has an element which isn't in B, then that means this set is non-empty. Likewise, saying that B has an element which isn't in A is the same as saying B set difference A is non-empty. So therefore, since this is true, or this is true, or both, then that means either this is true, or this is true, or both. So that means if we take the union of these two sets, our union is going to have to be non-empty as well. And why is that? It's because this set, the union, contains all elements of this set as well as all elements of this set. So since at least one of these two sets contains something, then their union has to contain at least some element as well. But what is this guy the same as? This is A symmetric difference B. So we've proven that asymmetric difference B is not empty. But this is a contradiction, right? Because we assumed it is empty. So therefore, our assumption that A was not equal to B was wrong. And therefore, the only conclusion must be that A and B are equal after all. Okay, so the moral of the story is if you want to tell if two sets are equal or not, you can just take their symmetric difference and see whether or not it's equal to the empty set. Here's another theorem that's not super duper obvious. It says that intersection distributes over symmetric difference. In other words, if you're an A and you're in exactly one of B or C, well, that's the same as saying you're in exactly one of these two sets. Either you're in both A and B, or you're in both A and C, but not both possibilities at once. Let's prove it. If X is in this set, what's that the same as saying? That's the same as saying X is in the first set and X is in the second set. Now, saying X is in the symmetric difference is the same as saying exactly one of these two guys has to be true. And now, here's the thing. Saying you're in this guy and you're in exactly one of these two guys, well, then that means either you're in this guy and you're in this guy, or you're in this guy and you're in this guy, but you can't be in this guy and in both of these guys. In other words, it's the same as saying exactly one of these two possibilities has to be true. Now, the first part is the same as saying x is in this intersection, and the second part is the same as saying x is in this intersection. Now, saying you're in this set, XOR you're in this set, is the same as saying you're in the symmetric difference of those two sets. Since these two sets have the same elements, they must be equal. Okay, so we proved that intersection distributes over symmetric difference, but what about unions? If I change all these intersections to unions, is that still true? Pause the video and try to figure out yourself if this is true. If it's true, prove it, and if it's not true, give a counterexample. Okay, well, I claim this is not true in general, and let me give you a counterexample to explain why. Suppose B and C are both the empty set, and A is the singleton containing the empty set. Well, since we're assuming B and C are equal, then that means we can change all these C's to B's, and we can check, is this true? Well, here's the thing. The right-hand side simplifies to the empty set because we proved earlier that the symmetric difference of any set with itself is just the empty set. Same with this symmetric difference here. This part has to be the empty set as well. So this part simplifies to A union with the empty set. If you take the union of any set with the empty set, it just simplifies to whatever this set is. So this simplifies to A. So if this is true all the time, then that means here A has to be the empty set. But that's not true in our case, since we chose A to be the set containing the empty set. So therefore, this formula here is not true in general. Here are all the theorems we proved today if you want to add them to your notes. You don't have to memorize these, but it's important to know how to derive them if you ever need them. Stay tuned for the next lecture on the axiom of the power set.